All right, in this lecture, what we're going to do is we're going to start talking about the last topic that we're going to cover in this class, which is tree structures. Tree structures are an interesting variation on the linked list, and they're used extensively and very powerfully because they provide a natural way in which we can structure divide and conquer problems. In our analysis of sorting and searching, when we looked at quicksort and we looked at binary search, we saw that this divide and conquer strategy was very powerful for being able to increase the efficiency of some of our computer science algorithms. So naturally, a data structure that mimics this would be potentially very powerful as well. And so that's what we want to introduce with the idea of tree structures and how we might use them. So what our chapter goals are to study trees and binary trees, to understand how we can use them to implement the data structure of sets, to understand a particular way of managing trees called red-black trees, probably the most complicated thing we're going to look at in the class. Think about the way in which we can traverse a tree, understand heap data structures, and then think about priority queues and sorting. Now there's this picture of a tree here is upside down because we use a metaphor of a tree in order to describe the data structure, but the way in which we draw trees usually has the root at the top of the tree when we draw the computer science structure. And of course, trees in nature have the root at the bottom and extend up to leaves. But we actually talk about leaves being at the bottom of our tree. So it's an unfortunate side effect of the way in which we use that metaphor. One way in which trees are used in sort of common parlance is to talk about a family tree. And often these are used in order to show descendants of a common ancestor. These can be drawn in different ways. For example, this one here. And so we sometimes like to use the language of biological trees or family trees in order to describe different components of a tree data structure. One thing that is true about the tree data structure is that it is hierarchical data. And we think about it as being composed of a number of different nodes, just like a linked list. But rather than being connected linearly, they're connected in a branching pattern. And so that means that each node has a sequence of nodes, not just one follow-on node like a linked list, but several follow-on nodes. And we call the root node as being that one node that exists at the beginning of the tree, the node that has no parent. And we call a leaf node any node that has no children. So it's kind of the root node is the top and the leaf node is the bottom. A tree only has one root node, but it can have many leaf nodes because of the branching structure. So let's look at what this might look like in one particular specific family tree. So this is a simplified view of the British royal family tree. We see at the top there's a common ancestor, George V, and several different children along the way. If we follow down that second node, we have George VI, who has a child, Elizabeth II, who has a child, Andrew, that has two children, Beatrice and Eugenia. So this tree structure, the way in which we draw this family tree mimics the way in which we think about computer science trees. We have one top node, we have several different children, and each of those children can have 0 or more children as well. Now, if you look at this, you can see that there's a relationship between the tree structure and the linked list. For example, if we were to just take one particular path from the root node down to the far left node, William, it would go George V, George VI, Elizabeth II, Charles, and then William. And that pattern of moving from node to node to node to node looks just like a linked list if we ignore all the other children. And so because of that, the code that we use to implement it is going to be similar as well. Now, I want to make a point here that this family tree, we like to talk a lot about the British royal family tree because it has specific sort of implications for government and it's very formalized. But the reality is that no one's family tree looks like this. And so if we were to look at the family tree, say, for American royalty, Thomas Jefferson, we can see that it's no simple branching tree. It has several different parents and roots and all kinds of combinations. Whether or not we like to talk about the complexity in families is another issue. This is the family tree that was developed based on genetic analysis that shattered the myth that Thomas Jefferson only had children with Martha Jefferson. In fact, he had children with a slave of his, Sally Hemings, as well. This is true in the complexity of family trees is true in my own family. When our family started participating in a DNA registry, Ancestry.com in particular, when you register your DNA, Ancestry.com shows you close matches, family matches. And through that process, we discovered we had a cousin that we didn't know, who was born out of wedlock and complicated our family tree by quite a bit. So the idea that a family tree looks like that idealized version of the British family tree is a myth, but it's something that's helpful for us to try and understand the way in which computer science trees are structured, because computer science trees, being a mathematical formalism, do hold to a much more specific structure. So here are some common terms that we need to know in order to work with a tree. We know the term node. A node is going to be one particular link in that tree. That each node in a tree can hold data as well. Just like a linked list, each node holds data and a link to the next node. Each node in a tree holds data and a link to all the children. A child is any node that has a parent node. A leaf is any node that has no children. So this would be like the bottom of the tree in some sense. An interior node is any node which is not a leaf, and so that can include the root node. A parent node is any node that has a child. A sibling is sort of where we use the computer science terminology. A sibling is any node that shares a common parent. A root is the node that has no parent, and by definition, each tree only has one root node. A path means a sequence of nodes that starts from one ancestor and goes to one descendant. It doesn't necessarily have to be a root and a leaf. It can be anything in between, but it is a path of direct descendants that is within a given tree. A descendant is a node that has a relationship with another node where you can find a path from the ancestor node down to the descendant. A subtree is any tree that is formed rooted in one of the interior nodes. And so, a large tree can have many and should have many, many different subtrees. And then finally, the height of the node is the number of nodes in the longest path from the root to a leaf. So those are some basic tree concepts that we need to understand. We're trying to get our head around what a tree is in the data structure sense. And so let's see if we can manipulate and work with this a little bit. Other places where trees exist in computer science are, for example, in the structure that you might have for files on your computer. So maybe you have structured your code for this class as in a folder called sample code, and then you have subfolders called chapter 1 and chapter 2. Each one of those folders has maybe sections or files within them. And so the folder hierarchy on your computer also exists in a tree structure as well. Sometimes that's hard to see because of the way the file interfaces will allow you to do search, or will show you the most recent files, or will show you all the files of a particular kind on your hard drive. But if you get rid of all those search functions on your hard drive, the basic file structure is as a tree. Similarly, we've seen trees in inheritance hierarchies. For example, maybe you have a set of classes where you're trying to keep track of quizzes like in Canvas. And you have some sort of superclass called question, and from question you have several different kinds of questions that might be asked on a quiz. Maybe a numeric question, maybe a multiple choice question, maybe a free response question. And those classes might also be subclassed. So these hierarchies, generally we see them all over the place. We use them to help organize information, and the tree data structure helps us to match a representation in computer science to a kind of model that we have about the world outside of the computer. So here's an example of some code, one way in which we can implement the tree. So in this case, let me see if I can shrink this down just a little bit. There we go, so we can see it all. That's pretty good. All right, so each tree is going to be represented with a class called tree, and we see that at the top here. And each tree has within it an interior class called a node. This is the same structure that we saw with a linked list, but there are going to be some differences here. You can see that as an instance variable within our tree, we have one particular reference to a node called a root. So within the tree class, we keep track of a root. This is analogous to the linked list keeping track of a first reference. When we create our tree and we call our constructor, you can see that the constructor takes a parameter called root data. And what we do when we create the tree is we first create a node that the root is going to point to. So we call the node constructor, and we put into the node, now called root, we put into that particular node the data that the user who wanted to start the tree asked to store at the root. And then we also initialize a set of children that that root node is going to have by creating a new array list to have several different children. Then the reference to the tree is returned back to the user, and the user can call methods on our tree, for example, to add a subtree. When you add a subtree, you take a second tree that you already have, maybe by calling a constructor, and inserting it as a child of the root of the current tree that you have. Now, trees are very, very recursive, and so getting our head around recursion was an important previous step that we had to work through in order to be able to work with trees. When we do tree algorithms, we're often doing them recursively. And just like a fern leaf, you can think of each one of the leaves as looking just like the bigger leaf and a smaller frame. Trees are the same way. We can take any given tree and look at its root, but we can also treat each subtree as if it was its own independent tree at the same time. So for example, if we wanted to ask what the size of a tree was, and we had a reference to its root node r, well, the size of the tree can be computed recursively. We say the size of a given tree is 1 for the node that you currently have in your tree, plus it's the size of each one of this node's children. Maybe it is maybe there's just a subtree of 1 as the first child, or maybe there's a subtree of 5 million. You don't know. But what you can do is you can call recursively each one of the subtrees, get the result back, and add them up, and then return them to the caller of your size method as well. Here's some implementations of methods that can do that for us. So notice in the first of all, notice that in the first case it is a method in the node class, and in the second class it's a method in the tree class. So what the tree method size is going to be, it's going to be people who are using our tree, and they'll construct a tree and they'll say, hey, I want to know what the size of my tree is now. And so that second method at the bottom is the one that we start with. First, we check to see whether our root node is null. If it's null, then we're a size 0 tree and we return 0. But otherwise, we're going to ask our root node to tell us what its size is. Now notice this isn't a recursive call because we're not calling the size method on the tree class. We're calling the size method on the node class. So that root.size calls the size method on our node class, which is in the top block here. This is the recursive call. We start with an aggregator variable sum. We say that's equal to 0. Then we iterate through each one of our child nodes that's kept track of in an array list called children. And one by one, we increment our sum aggregator variable with the recursive call asking each one of our child nodes to tell us how big it is. So one by one, we go through each one of our child nodes and we say, hey, recursively tell us how big you are. And when you give us an answer back, we're going to keep track of that. Finally, when we get out of this loop, we add 1 because of the node we're currently in, and then we return that. The node class doesn't know whether it's returning it from a recursive call to another node class or whether it's returning it to the original tree call as well. But it doesn't matter because it has calculated the size of itself plus all of its children, which is what it was asked to do. All right, so let's take these ideas and see if we make sure we understand them with a little assessment quiz to follow in Canvas. Thanks for your attention.